797K. It's Thursday, February 25th. The exam is tomorrow. The plan today is to go over the any questions that you might have over the practice exam and about the format of the midterm exam. So the first thing I'm going to talk about is the format of the midterm exam. It is going to be on paper. There is going to be no cheat sheet. I will provide a piece of paper that will kind of serve as a cheat sheet. It'll have a Galois field table on it, things like that. But to remember the formulas for MTTF, remember the formulas for overhead. That's part of the understanding that what we've talked about in the class, and they're not very difficult. Again, we can go through the thing here in a moment here and go through what the calculations are. And remember, it's a straightforward rule of thumb that you're looking at as to how to calculate the mean time to fail for a RAID volume, right? Anyhow, there will also be a scratch paper. I'm going to give you a one page. It's going to have on one side, it's going to have a log anti-log field for a Galois field. So I have the table, and then the back side of that sheet will be completely blank, and you'll be able to fill that in and use it however you want to. So I'm going to go ahead and, as per the student's request, how do we do questions 8, 9, 10, and 12 again? So 8, what is the overhead for an 8+3 wide drive RAID RTP volume? So overhead, let's go ahead, file new. And we'll just type it in here, and we'll go ahead and give us a bigger font so that people can read this online. Overhead. It is the number and so if you look at notes, if you have notes from previous students from previous semesters, I didn't have this same formula because at NetApp Corporation, we had the way we wrote the formula was the total number of drives over the number of data drives. So you have this extra stuff that you buy. But this is a legitimate way to report overhead, and it turns out to be that's the way that the industry has moved since I left NetApp Corporation. And so we're going to use that. Basically, I want to store, I have 3 terabytes worth of data. I can go out and buy drives that hold 1 terabyte each. So I could go out and buy 3 drives, put my 3 terabytes of data on, everything's fine. But if I want to protect that by getting an extra drive, that extra drive is what we call the RAID overhead. It's the extra data storage that I buy in order to get the RAID protection. So if I go out there and want to store, 3 terabytes worth of data with a RAID 4 volume, I'll buy 1 extra drive. I'll have an overhead of 1/3, right? So, say I have 4, 3 plus 1, call that RAID 4, 3 plus 1, or RAID 5, 3 plus 1, right? Then the overhead is 1/3 because 3 of those drives in that, so RAID 4 with 4 drives. So it's a RAID 3 plus 1. That is 3 data plus 1 parity. Overhead is 1/3. So if we have a RAID 10 with 3 plus what? We're going to build a RAID 10 volume. What's it going to be? 3 plus, how many parity drives do I have in a RAID 10? 3. I have 1 parity drive for every, because RAID 10 is a striped RAID 1. RAID 1 is there's just a mirror drive for everything. I don't really have a parity. I just have a full extra overhead. So the overhead in this case is 3/3 equals 1. In this case, it's 1/3 equals 0.3333. On the midterm, I'm going to ask you to write the overhead just as a fraction. You don't have to go any further than that. Just write it as a fraction. Don't have to put the decimal down, okay? So a RAID RTP with 11 drives. What's the overhead on that one? RAID RTP is RAID triple parity. So there's 3 parity drives. So that equals X plus 3, right? Which is going to be 11 minus 3 is 8. So that's going to be 3/8, right? Is the overhead. Okay. Any questions? I'm going to go back to the chat in here online. No, I see no one else has joined online. Okay, that's fine. So any questions about that? The student, I don't know if the student that posted that request is in the classroom. If not, this recording we'll try to get that available as soon as possible after class. Let's go back here. Question 9 and 10 are on, question 9 is MTTF, right? And question 10 is we're generating an anti-log table. So we're going to go ahead and build an anti-log table in a minute. So let's go ahead and do question 9. MTTF for a volume is Q8. Okay, there we go. Q9, MTTF is a fraction. Numerator is raised to the power of how many drives have to fail. Right? If I have a RAID 1 volume, how many drives have to fail to kill it? Both of them, 2, right? If I have RAID 10, how many drives have to fail to kill a volume? 2. It's the right 2 of them. RAID 10 can survive more than 2 drive failures. Right? If you have a RAID 10 with, say, just 4 drives, right? So you got 2 pairs, and this drive fails, and this drive fails, your volume's still alive. You failed 2 drives, right? You can survive 2 drive failures, right? In order to kill it, that 3rd drive is definitely kill it. Or if you fail this drive and then this drive, you've died after 2 drives failed, right? So it's, in the calculation is how many drives we have to fail to kill a volume, this smallest number we pick, right? The denominator is denominator. Well, let's have some fun and spell it that way. Denominator. Yeah. Yeah, we'll have some fun spelling it there. Denominator is how many drives can fail first times so however many drives we need to fail to kill that, right? We actually have to kill that many drives. Fine, we'll go ahead and fix it. And so if we have a volume that can handle 3 drive failures, then we'll have MTTF raised to the power of 3. I'm sorry, if it can handle 3 drive failures, it's got RAID triple parity, for instance, then it has to have 4 drives to fail. So in that case, the numerator is MTTF raised to the 4th power, and the denominator is however many drives you have times 1 less than times 2 less than times 3 less than. So you've got four different figures in there because the 1st drive, 2nd drive, 3rd drive, and then that 4th drive fails, and then you're dead, right? And then times MTTR. And the idea is that this is a simple calculation. It's a rule of thumb. You're just basically saying your 1st drive fails. As long as you get the drive repaired before our 2nd drive fails, everything's okay. If 2 drives fail and your RAID volume can handle 2 drive failures, then great, right? So MTTF for on the question was RAID RTP or RAID 5 MTTF for an MTTR. For a 6-drive wide RAID 5, given drive MTTF is 4 hours and MTTR is 1.5 hours. So it's a RAID 5. So the numerator is MTTR squared, right? And the denominator is size. And when that second drive fails, the thing is dead. So our calculation is going to turn out to be 4 squared, or 16. And on yesterday's class, I put a typo in there. I put 4. I was intending type 4 to the raised to the power of 2, and I typed 4 raised to the power of 4 was a typo. But then we had total of drive 6, and then 5, and then 1.5, which equals 16 over 30 times 1.5, 45, and that's the answer. Right there on the exam, you can stop right there, okay? If you want to convert that into hours, you can go ahead and do that, but we're doing it with simple fractions, so you don't have to worry about using calculators or anything like that. We're just going to have to do some simple multiplication. How about MTTR power 2 divided by the total number of drives, right? Ooh. MTTF squared, yes, MTTF. So basically, that first drive fails, and then the time the expected time to take for 2 drives to fail on there is the MTTF raised to the power of how many drives you're having to fail, right? So if we had a RAID 5 or maybe a RAID 0, we just kept reading data until everything was dead. What would be the time for every single drive in there to fail? It'd be just the MTTF raised to the power of however many drives there are, right? It's when you lose your redundancy is when the volume fails. So we're doing the volume failure calculation, right? And again, this kind of simple formula actually applies equally as well to airlines, right? If you've got a jet plane with 4 engines and the mean time to fail on an individual engine is X, how long before the plane, can no longer keep flying, right? And has to land. Things like that. It's not just RAID volumes that do this. Let's try an example just for grins. We didn't do RAID 10, but how about RAID 10? Okay. Let's say we have MTTF is 10 hours, and the number of drives is 6, and MTTR is 1.5 hours. So what is the formula going to be? Well, it's a RAID 10, so we have to fail 2 drives, right? So the top is 10 squared, right? And the denominator gets a little weird in here. It is any one of those 6 drives can fail, right? And then the next drive that fails, if it's in a different RAID group, it doesn't matter. So there's only 1 drive available to fail, it will kill it, right? So if the second drive that fails is in the group that first drive already died in, that's when we're seeing an actual volume failure. And then, of course, that's 1.5, right? And that's going to be 100 over 9, okay? So that's the RAID 10 formula. That's a little weirder because, again, we're not just saying any one of the remaining drives can fail. We're saying that a specific drive has to fail. Back to the midterm, we said, what about a RAID RTP with 6 drives, same MTTF, same MTTR? What's the numerator? Well, RAID RTP can handle 3 drive failures. So that 4th drive has to fail. So we're going to have 4 raised to the power 4. That's going to be 4 times 4 is 16, times 4 is 64, times 4 is 256, right? Say 64, no, 100, yeah, 256. So 256 is the numerator, and the denominator is going to be 6 times 5 times 4 times 3 times 1.5. Okay. Let's go ahead and just write the numbers down here on these. Grammar. No, that's a mathematical formula. Stop it. RAID RTP volume with 6 drives. And again, this is, let's go ahead and drop that down there where we don't get confused. So again, our MTTF is 4, our MTTR is 1.5. So this is RAID RTP can handle can handle up to 3 drive failures without failing. So it's going to be 4 raised to the power of 4 over 6 times 5 times 4 times 3, because we have to fail 4 drives, times the MTTR is 1.5. So that's our formula for RAID RTP, right? What about a RAID 6 PQ volume with 6 drives, same MTTF and same MTR? This is going to be 4 to the power of 3, because RAID 6 handles, P to Q parity, so it's 2 parity drives. So when that 3rd drive fails, we're dead. And we're going to have 6 times 5 times 4 times 1.5, right? And you can do the math yourself. Again, that's going to be 64 over 6 times, well, that's going to turn into, we can divide that by 4 again, bring that back down to 16, just to eliminate that 4. And it turns out that the MTTF of a RAID 6 PQ with that particular configuration is identical to the RAID 5 volume, right? Because we happen to have picked the numerator that is canceling out with the denominator down here. So this would be, actually, this would be 64 over 6 times 5 times 3 times 1.5, because we can cancel out some of our things and make our calculations a little simpler. All right, blah, 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 blathering. Question 10. Oops. Get down here. Question 10, they asked us to say this. Again, question 10, we're generating log anti-log tables, right? We're using this primitive polynomial, x to the 5th plus x squared plus 1. What is that? X to the 5th is 32 plus 4 is going to be 36 plus 1. So we can say that is 37, or that is 1, 4, 3, 2, 1, 0. So 32, 16, 8 times 4, 2, and 1. And that's our binary primitive polynomial, right? And there's going to be, the test is actually going to start with 2 binary hexadecimal formula conversions like this. So we're going to have a couple questions to just do that, to show that you can get the conversions done. So we just generated hex 11, which is decimal 17. What is the next anti-log? So the procedure we take the number that we just generated and we double it. If we're out of the range, we XOR with primitive polynomial, and that will bring it back into range, right? So we take 17, 0, 1, 0, 0, 0, 1, we double it, becomes 1, 0, 0, 0, 1, 0. Again, 17 doubled is going to be 34, right? Then we see that that is outside the range of our table. That is bigger than 32, bigger than 31, actually. So since it's bigger than 31, we have to XOR it with the primitive polynomial to bring it back into range. So 1001 XOR 100101 equals, we're going to take this is going to cancel out. This is going to be a 0. This is going to be a 0. This is going to be a 1 XOR a 0, a 1 XOR a 0, and a 1 XOR a 0 equals 111. 7 decimal, hexadecimal, right? So that is the next antilog. So for the next question here, we said, okay, well, how about if we just generated 20? And this is 20 in decimal, so that's 16 plus 4. What is the next antilog? So again, the procedure is double and XOR, right? So, and the XOR is only if necessary. So 20 doubled is 40, which is 1, 0, 1, 0, 0, 0. And that's 32 plus 8. Okay. And then we see that that is outside the range because it is decimal 40, which is bigger than 32. Right. And so we have to XOR with our primitive polynomial, which is, again, 37. And now we can out here, how should we see? We've got a, this one is on, this one is on, here's off. And so we get a 1101, right? Which is what? That's 8 plus 4 is 12 plus 1 is 15, right? 13. Okay, so what comes next? After 13, we double 13 and we get 26. Is that outside the range? Nope, it's not. We're fine. We double 26. $52. We go ahead and take that. So we got, this is 110100 XOR again with 100101, right? And we get another number, we bring ourselves back into the field. So it's just this constant building the table. Straightforward, not difficult. The dog is sitting, standing, whatever, right? So we have a Jupyter notebook out here that we can load up. And it's worth playing around with this if you haven't yet, because this will help you understand what's going on straightforwardly. It's not difficult. It's just, you know, different from what you've had to do to this point. So we're generating our tables. We're going to generate a table of size 5. And we're going to use a primitive polynomial of 37, right? We're going to go ahead and go down here real quick and delete this and delete this because we don't want to mess with those. All of our tables are all filled in with the existing stuff, so we're going to go ahead and run the whole thing again. Okay, so we're building our table. Say we just generated 20. What's the next value? 13. We said here, we just generated 17. What's the next value? 17 turns into 7. And you notice that 13 doubles to 26, 26 doubles to 52, which actually doubles back to 17. So actually one right before the other, right? So, you know, we can start anywhere in the table and just keep building from there, right? This is why if you look at Dr. Tarivo's University of New Brunswick website where he has the primitive polynomials. This is not a table of primitive polynomials. This is a table of irreducible polynomials, things that can't be factored. And some of these are not primitive. They don't build the full table. If we tried to use 31 to build a Galois field table, and we can go ahead and try that, what do we say? 5 and 31, right? Arg. And run that. We'll get an error as we're generating our tables. What we've built is half. Nope, it just kind of quit in the middle. So I thought I'd fix that so it wouldn't go out of range. But yeah, so the problem is we're trying to build a GF log. It can't build it because there's no value filled in, right? So we have to initialize the table with something other than zeros in order to do that. So I guess we can't show that one right away. But the point being that actually if you start, it'll go 1 through 5, and then it'll repeat starting at 10 and repeat starting at 15 again, right? And so some of these irreducible polynomials can be useful. We get down to this number right here, 283. This is actually an irreducible polynomial used for cryptography, for the RSA algorithm. This is the value that's used for RAID algorithms because this needs to be a primitive polynomial, right? So this table is actually more than just primitive polynomials. And you can try experimenting with building just the antilogs and see what happens as you just count through different values. Okay, so back here, last question was on question 12. You wanted to know what's going on with question 12. Question 12 is RAID DP. Okay, so I'm going to go ahead and pick my random number between 6 and 10. I'm going to use 5. Okay. So I'm going to say let's go ahead and copy that. And we'll probably have to shrink things on here. Or maybe not. There we go. So we're going to do 5. So how many data drives is 5? That's 0, 1, 2, D3, and D4, right? That's 5 drives. And then P and DP, right? And so let's go ahead and we'll put in here, we'll call this the segment number or the block number. So how many segments are there? 0, 1, oops. 1, 2, 3, 4. That's a single extent. There are exactly as many segments or blocks in a diagonal extent as there are a number of data drives. 0, 1, 2, 3, 4, and that would repeat. 0, 1, 2, 3, 4, so on, right? It just keeps going. Diagonal stripe 0, and the segment number is in fact identical on the diagonal parity. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. That is the piece of the diagonal stripe that is on the diagonal parity drive. It's just exactly the same as a segment number within the extent. And then the data drives and parity drives that go to make that up are starting on where the drive and the block number are the same. Drive 0, block 0, drive 1, block 1, drive 2, block 2. Those are all diagonal stripe 0. Okay. B is going to be basically drive 5. That's what we'll call it. So when the drive number is 1 bigger than the segment number, that's diagonal stripe 1. 1 minus 0, 2 minus 1, so on and so forth. 1, 1, 1, 1, and 1. And then we go up here and we start back again with 2. Wraps around. And finally 4. And we can take that data, and since we're on a nice word processor, we can just Control-C, Control-V, and fill it, and it repeats over and over. And what diagonal stripe was this part of? Nothing. It's not part of a diagonal stripe, right? Okay. I hope the person's question will be answered either in person or on the recording. Let's see. No questions. No questions. No questions. Please post. Oh, here's a question. Please post all the recorded sessions up to now. Get that up there before we go home today, I guess, huh? We can do that. Okay, someone else has doubts on 8, 10, and 12. We went through those. No questions, no questions, no questions. Nothing. All right, I think that was mostly it. I think I accidentally exited out. Okay. So if anybody in the room has more questions on that, I will happily address them. I have been putting the exam together. So I actually kind of rearranged the structure of the exam from the practice exam. It's not going to be just straightforward copy of that, but it's going to be real similar to it. A few of the questions will be different. I just need to go in and plug in the individual values for these questions, and we'll be ready to go. So it should be a fairly straightforward exam, nothing difficult on it. And it's just a matter of getting things done cleanly. The Hamming code decode, I've tried to put in a bunch of blanks on the exam to do it step by step by step. Go ahead for the P1 calculation. I want you to write down the string with X1, X0, X1, X0, whatever it is, just put X's where there's not a bit that you're counting, right? So I can see if you made a mistake, what mistake you made was, and not have it propagate to the next step. And then the number of bits that you count and whether the parity is even or odd, those are two separate answers. So don't put down 1 or a 0 for the number of bits if there aren't 1 or 0 bits that are ones in there, right? If there's a 3, you don't take that modulus 2 yet. You go ahead and tell me whether that's an even or odd parity, indicating whether there's an error or not, right? Every semester, there's at least one person that tries to encode the decode message. So make sure you know the difference between encoding and decoding, and don't try to encode when you're doing a decode, which is on the exam. Okay. That's basically it. If no one has any more questions, anybody in the room? I see nobody signed up online. Are you online? The meeting? I did join the right meeting, didn't I? You checked it earlier? Yeah. Okay, good. Yeah. Okay. Yeah. I'm just kind of interested that no one signed up online. So I guess everybody that wanted to sign up got it yesterday. So there's our recording again. We'll call that good. And we can go ahead and end that recording.